Asymmetric energy term. Asymmetry means the asymmetry in the number of neutrons and protons. Okay. So basically what it means is that this term is dependent on the excess numbers of neutrons in the system. So if there are higher number of neutrons, then this term will add to the contribution. Okay. So and it decreases the nuclear binding energy. So this term is proportional to n minus z by a. Okay. So how does this formula come about? So we consider a medium or heavy nucleus of mass number a. So mass of such a nucleus can be written as, we already find this formula, m is equal to zmp plus n mn minus b, where b is your binding energy. Okay. So substituting all the values for binding energy. So in case of b, we'll replace by bv, bs and bc. So here what it okay. Here also n is what? N is the number of neutrons. Okay. So n can be replaced by a minus z. Okay. That is number of nucleons minus number of protons. So you will get the number of neutrons. So that is why the formula is of this form. Okay. Again, here there is a term for z and here there is a term for z. So the z term is combined and you get AMN, that is the first term, number of nucleons and mass of neutrons, then minus Z Mn sorry, Mn minus Mp, number of neutrons minus number of protons. So basically this is the difference of mass between neutron and proton. Okay. Now minus Av into A, this is your volume term, minus As into A raised to 2 by 3, this is your surface term, and Ac into Z minus 1 by A raised to 1 by 3, this is your Coulomb term. Okay. So because B is minus, so this term is minus, and this becomes plus and this becomes plus. Now here we see that this equation has two Z dependent terms. So this is one term on Z and this is another term which is dependent on Z. Okay. Which are opposite in sign. So this is positive and this is negative. Sorry, this is negative and this is positive. So what we can do is, because these are opposite signs, if we differentiate M with respect to Z, okay, and if we set equal to 0, we can find the value of Z. We can find the value of Z for which mass will be minimum. Okay. See, what he is trying to do is differentiating on the basis of so see, this is just an equation. So if you plot a graph of M versus Z, you will get a graph. So what we are trying to do is, without plotting the graph, we are trying to find the minimum value of M, okay, for a given Z. Okay, so that is simple. You just differentiate M with respect to Z and put it equal to 0. 0 means the lowest point or the highest, maxima or minima. So because M is minimum, M is the mass, okay, so it will correspond to the stable mass number. The minimum value of M will of course be expected to correspond to maximum stability for that Z value. Okay, so what we are expecting कि उस Z यानी number of protons के लिए the system is stable, उसमें decay नहीं होगा. Okay, so example दिया हुआ है. For example, if you put A is equal to 2.6, okay, 216, sorry, then the answer is the which gives a M, and hence the stability for Z is equal to 3, which is absurd. Okay, so इस equation में अगर if you are substituting A is equal to 216, okay, then what we are finding is that the stability is found for Z is equal to 3. यानी Z is equal to 3 क्या होता है? लिथियम. ओके, जबकि A is equal to 216 में लिथियम कहीं नहीं आता है. So this is a wrong answer. This is not supposed to happen. So we are missing some important information. Okay. So we don't know what this term is. Okay, the sign of so this term is such that the sign of this term has to be such that to increase Z for a given A, it must produce a deficit in the nuclear binding energy. So I mean this term should decrease the binding energy for increase in Z. As Z increases, this term should decrease the binding energy. Okay, so now once again we look back to we remember that till now we have been comparing the nucleus with a liquid drop. Okay, but we are forgetting one important concept or one important difference between a liquid and a nucleus is that a nucleus is a quantum system, and a quantum system has quantization of energy states of individual nucleons. Okay, but now nucleons are what? Neutrons and protons. Protons are fermions. We know that protons are fermions, and we know that neutrons are also fermions. Okay, so basically Pauli's exclusion principle is applicable to them. Okay, so now let me reduce this. So just look at this figure. These are all the energy states. Okay, the horizontal lines are all the energy states, and in one we are showing the energy, the proton occupation, and in the another we are showing the neutron occupation. Okay, now if we put Z and N in a nucleus, the lowest Z energy levels will get filled up first. Okay, so so as we know that the neutrons and protons with lowest energy will be filling up the lower levels. Okay, as you add them up. Okay, but by Pauli's exclusion principle, the excess neutrons must go to the previously unoccupied quantum states. Hence, the first Z quantum states are already filled up with protons. These excess neutrons are occupying higher energy quantum states and are consequently less tightly bound than the first two Z nucleons. Okay. So what the author is trying to say is that, okay, let us say we'll consider these numbers. This is 8, 16 and 420. If I say that my system has A is equal to 20 nucleons available. Okay, so what is happening, and this is 8, yes, okay, and say my number of Z, A is 20 and my Z is fixed. Z is equal to 8. Okay, so what will happen when you are creating the nucleus, and we are remembering the Pauli's principle. So this is one state. In this one state, two fermions of opposite spin can stay. So one proton, another proton. Okay, so parallelly there will be one neutron, another neutron. These both are of opposite spins. Okay, so again one proton, opposite spins, one neutron, another neutron, opposite spin. So 4 is occupied. Then again one proton, opposite spin, one proton, one neutron, another neutron, opposite spin. So one proton, opposite spins, one neutron, opposite spins. But now 8 means Z occupied, whatever is Z has been completely filled. Okay, so since our system has only 8 protons, these 8 protons are already filled up, and corresponding to these 8 protons we have 8 neutrons available, so these are also filled. Okay, so now but we still have 4 neutrons extra available. Okay, so they have to be filled on the upper state of neutrons only. Okay, so they will be filled here. So these neutrons are occupying higher energy quantum states. Okay, these are occupying higher energy quantum states, and there is no corresponding proton for them here. Okay, we expect that these four form a proper interaction pair. Okay, so here for these neutrons there are no protons available. As a result, they are less tightly bound than the first two Z nucleons. So this is Z and this is Z. So this whole number is 2Z. So beyond the first two Z nucleons, the other nucleons that are left, they are occupying higher excited states, higher quantum states, and hence are less tightly bound. Okay. So this asymmetry in neutron or extra number of neutrons gives rise to a destructive term in the nuclear binding energy, and it is called the asymmetry energy. Because there is no symmetry between the numbers of protons and neutrons, this term is called asymmetry. Okay. So the neutron asymmetry therefore gives rise to a destructive term in nuclear binding energy and is called asymmetry energy Ba. Okay. So to get the form of Ba in a simple way, we know that the number of excess neutrons is n minus z. Okay, so n minus z will give you the extra number of neutrons. Okay, and if you divide it by A, then you get the extra number of neutrons per nucleon. Okay, since the total number of excess neutrons is n minus z, the total deficit in nuclear binding energy is proportional to the product of this. Okay. So now as you have the, let us say n minus z is the total number of extra neutrons. Okay, then the nuclear binding energy will be proportional to the product of this. It will be proportional to the square of it. Okay. So that is why Ba it will be equal to A n minus z whole square by A. Okay. Now instead of n, you can write A minus z. So it will be A minus 2z whole square. Okay. And AA is called the asymmetry coefficient. Okay, this is called the asymmetry coefficient, and empirically its value is 19.8 MeV. Okay, so this is found. Now if we go to the previous example of A is equal to 216, then what do we find? So now using this value of AA and putting dm by dz equals 0, we now find that for A is equal to 216, M gives a minimum for Z is equal to 80. Okay, so now if you put A is equal to 216 and you add this term in the previous equation, then we get that the minimum value of M is for Z is equal to 80, which is a reasonable answer. It is it matches with the experimental results to some extent. Okay, thus by incorporating a pure quantum mechanical effect in binding energy, one can go beyond the liquid drop model. So this is basically a quantum effect. Okay, and it is not dependent on the liquid drop model. So actually the three properties which are associated with the liquid drop model are volume term, surface term, and Coulomb term. All these three are closely linked with the liquid drop model. You can consider asymmetry term as a correction to the binding to the liquid drop model. Okay. Now how long is this? Okay, we can try. So now till now, so does anybody have any query with regard to asymmetry term?
સર લિથિયમ વાળું ઉદાહરણ તો કઈ ખબર ન પડી.
ના ખબર પડી?
લિથિયમ વાળું ઉદાહરણ હતું.
હા, લિથિયમ વાળું એટલે બેઝિકલી શું છે કે આપણે પાસે જેટલા ટર્મ્સ હતા એ બધા ટર્મ્સ આપણે અંદર સબસ્ટિટ્યુટ કર્યા બાઇન્ડિંગ એનર્જી માટે. ઓકે, અને એના બેસિસ પર કેલ્ક્યુલેશન તમે કર્યું. ઓકે, તો કેલ્ક્યુલેશન તમને શું ફાઇન્ડ આપે છે કે આ સિસ્ટમમાં જો તમે A ની વેલ્યુ તમે 216 સબસ્ટિટ્યુટ કરો તો તમને મિનિમમ ક્યારે મળશે? જો તમારો Z3 હોય, એટલે Z equal 3 એટલે કઈ એલિમેન્ટ થયો લિથિયમ થયો, બરાબર. હવે A is equal to 216 હોય, it means શું છે કે નંબર ઓફ ન્યુટ્રોન્સ પ્લસ નંબર ઓફ પ્રોટોન્સ is equal to 216, બરાબર. તો કોઈ બી સિસ્ટમમાં જો 216 ન્યુટ્રોન્સ કે પ્રોટોન્સ હોય તો એનો જે શું કે એલિમેન્ટ નંબર 3 તો ના જ હોય કોઈ બી કેસમાં, બરાબર છે. એનો જનરલી જે આન્સર છે, હા, એ આ જે છે dm/dz વાળું એ આપણે નેક્સ્ટમાં કેલ્ક્યુલેશન આખી આવે જ છે, એટલે વધારે ડિટેલમાં ખબર પડશે કે કેવી રીતે વર્ક કરે છે. ઓકે, till now all our energy terms have involved a smooth variation of B. Okay, whenever proton number Z or neutron number are changed. Okay, in the last term we have seen that B by A against A plot shows several links and there is evidence for favored pairing. Okay, whenever N or Z becomes equal to 2, 4, 8, 20, 50, 82 and 126, the corresponding nuclides have large binding energies. Okay, so અત્યાર સુધી જેટલા બી આપણે આઈડિયા હતો પ્રોપર્ટીઝ, whatever the information that we know regarding the properties, okay, based on that we are adding one by one terms to the binding energy. Okay, so now normally the variation is very smooth, but we know that for certain pairings, okay, that is for certain value of Z and N, okay, the binding energy becomes high. These values are 2, 4, 8, 20, 50, 82 and 126. Okay, for these values of N and Z, okay, the binding energy is very high. So we want to know why. Okay, so this fact does not appear in liquid drop model because we have omitted the intrinsic spin of the nucleons and the shell effects. Okay, so this omission. So basically to explain this you generally need the intrinsic spin of the nucleons. Okay, but since a liquid does not have an intrinsic spin, we have not added this term. Okay, so to compensate for this term, it is partly corrected by adding a pairing energy term. Okay, so what we are adding is we are adding a pairing energy term B pairing to nuclear binding energy. So so a nucleus can be classified into 4 possible groups. Okay, now A is what? Number of nucleons, it is total number of nucleons. Okay, Z is number of protons and N is the number of neutrons. A, actually you can write it like this also, A equals and plus, okay, A equals Z plus N, okay, and number of stable nuclei. So this is basically experimentally observed behavior. Okay, so here is saying A is equal to even, means total number of nucleons is even. So for example 2, 4, 6, 8, 10, 20, all the even numbers, if your nucleons total number is either equal to any even number, okay, so that is what is saying, any even number. In that case, if Z is even and N is even, the case where the number of protons is also even and number of neutrons is also even. For example, for oxygen Z is 8, oxygen is 8, okay, and if the number of neutrons is also 8, okay, so then 8 plus 8 is 16, so A is also even. Okay, so we are talking about that kind of example. If that is possible, then I mean all such combinations, so for 16, 22, 33, whatever number it is, if it is A is even, Z is also even and N is also even, in that case the total systems which are found to be stable are 165. Okay, now another thing, if A is odd, okay, so let us say 235, okay, 235 uranium, okay, now Z is even, so uranium 235, for uranium 235 the number of protons is 92, so it is even. Okay, so rest is the number of neutrons. Since this is odd, this will also be odd. So when the number of nucleons is odd but the number of protons is even, okay, then the number of stable nuclei is 55. Okay, experimentally observed. Okay, now again one more example. If the number of nucleons is odd, okay, and number of protons is odd and number of neutrons is even, okay, in that case the number of stable nuclei is 50. If A is even, Z is odd and N is odd, okay, both are odd, in that case only 4 stable nuclei are seen in nature. Okay, practically observed, only 4 systems are present. Okay, so what does this tell us? That there is certain combination which is acceptable. That is, if it is even, then N and Z are both even, then the system is stable. Okay, if it is even and 2 terms are both are odd, okay, so let us say example of even will be let us say 16, okay, and your what you say is the number of neutrons, number of protons is 7 and number of neutrons is 9. Okay, so 7 and 9 is 16 and A is 16. In that case the number of systems with this kind of behavior are very less. Okay, now nucleons with odd number are acceptable. Okay, in this, if Z is even and N is odd, and if Z is odd and N is even, both cases are acceptable. The only problem comes with this system last, the even with odd combination. These kind of nuclei are least stable. Please mute yourselves. Okay. So basically this is the odd even effect. I think time is up. Okay, just a minute. So basically we will consider the pairing term, so odd even term. I think it will take some time, so we'll continue in the next lecture regarding this concept. Please revise, and I'll ask questions regarding whatever is this asymmetric term and other terms, semi-empirical Weizsäcker formula. Okay, see you in the next lecture. Now anybody has any doubts?
सर अगर हम कोई और बुक से पढ़ रहे हैं और उसमें एक्सप्रेशन थोड़े अलग दिए हो तो वो लिख सकते हैं एग्जाम में?
बुक अपने बुक अगर टेक्स्ट बुक है तो चलेगा, और दूसरी बुक है तो तुम्हें जस्टिफाई ज़्यादा करना पड़ता है. आई प्रीफर इंडिपेंडेंट बिहेवियर, बट अपना यूनिवर्सिटी ऐसा है ना कि दे प्रीफर के एक स्टैंडर्ड बुक को फॉलो किया जाए. उससे बाहर जाता है तो देयर इज अ रिस्क के अगर तुम सही भी लिखा हो फिर भी दे माइट नॉट गिव यू मार्क्स. ओके, मुझे तो कोई इश्यू नहीं है, बट इट रिक्वायर्स के हाँ जो चेक करने वाला है अगर उसको पता नहीं है कि तुमने ये आंसर कहाँ से लाया या उसने वो सब बुक्स देखी नहीं है तो नॉर्मली दे वोंट गिव मार्क्स, ऐसा रहता है. सो इवन आई कैन टेल यू प्रॉपर एग्जाम्पल, ये टेक्स्ट बुक है तुम्हारी, राइट? तो अपने 2-4 सेमेस्टर में मीन्स 1 to 4 सेमेस्टर में हम जनरली नीरव से पढ़ते हैं, जबकि टेक्स्ट बुक अवेलेबल है. तो काफ़ी बच्चे होते हैं जो टेक्स्ट बुक को रेफर करके लिखते हैं, तब भी क्या उनको मार्क्स नहीं मिलते हैं. क्यों? क्योंकि उन्होंने नीरव को फॉलो नहीं किया, क्योंकि बाकी के सारे बच्चे नीरव फॉलो करते हैं. तो गड़बड़ ये मीन्स क्या है, एक पैटर्न फिक्स हो गया है कि सारे 1 to 4 में तो बेसिकली नीरव को ही ब्लाइंडली फॉलो किया जाता है. गलती है तो गलती छापो, ठीक है? सो माय सजेशन इज कि तुम वो सबसे, इफ यू वांट टू अंडरस्टैंड द टॉपिक और दूसरी बुक से तुम्हें समझ में आता है तो यूज इट फॉर योर अंडरस्टैंडिंग, लेकिन एग्जाम में तो वही लिखना है जो टेक्स्ट बुक में दिया हुआ है, ठीक है? ताकि परेशानी ना हो. मीन्स काफी बार क्या होता है कि यू आर करेक्ट बट यू मे नॉट गेट मार्क्स, ऐसा हो. दैट इज बेटर टू बी ऑन द सेफ साइड. तुम अपने नोट्स बनाना चाहते हो तो यू कैन यूज दैट मटेरियल, इट्स नॉट एन इश्यू. ओके। लेकिन इसको फॉलो करो, या तो फिर व्हाट यू कैन डू इज इंटरमीडिएट स्टेप्स अगर डिराइव किए हैं उस मटेरियल में, तो देन यू कैन सब्स्टिट्यूट एंड राइट इट इन दिस फॉर्म। टर्म्स का जो लेबलिंग और वो सब है, ठीक है, कहीं पे ये B1 B2 B3 दिया होगा, B4 B5 दिया होगा बाइंडिंग एनर्जी के लिए, इंस्टेड ऑफ दैट यू कैन जस्ट रिप्लेस के BV है BS है उस तरह से। सो इवन इफ द टर्म्स आर सिमिलर देन ऑल्सो इट विल बी ए लेस ऑफ अ प्रॉब्लम। ओके, तो टर्मिनोलॉजी है सिंबल से सेम रखो तो भी इट शुड नॉट बी ए प्रॉब्लम, मैं ऐसा सजेस्ट करूंगा।
ओके सर, गॉट इट।
हाँ, और किसी को कोई है? ओके, यू मे लीव।